All right, let's see. So we've got 4 of these integrals to convert into polar. So first thing to do is set up the region. So let's see. So do a little sketch. We've got x going from 0 to y. So here's x equals y. And we're doing x, so we're going in that direction. So we're going from 0 to y like this. And then this other one here tells me that this takes place between 0 and 6. So I guess we stop up here at 6. And so there's my region. It's this triangle. Okay, so now I need to set this up in polar. So I'm going to think of it as being filled out with little radial lines like this. And each of these stops on this, each of them starts at 0. So we're going to have lower bound at 0. And then we're going to go up to this one right here, which is y equals 6. So that's r sine theta equals 6, or r equals 6 cosecant theta. So we've got 6 cosecant theta. And then this is going from pi over 4 to pi over 2, like that. So we've got pi over 4 to pi over 2. Okay, and so then x becomes r cosine theta in the integrand, and then we've got a Jacobian making that an r squared, and then dr d theta. And so then to integrate this thing, let's see, so we can integrate the r part, and so we have bringing along the outer husk just for grins, cosine theta times r cubed over 3 evaluated from 0 to 6 cosecant theta. And rapidly running out of room here. And so then this is going to be, let's see, so substituting in at the lower end, we just get 0. And at the upper end, we're going to get 6 cubed, which is 216. 216 divided by the 3 in the denominator gives us a 72. And then we have the integral of cosine theta cosecant squared. Still with the same bounds. And so let's see, so then that integrates up to minus cosecant squared. So let's see, so this is over 2. So we get 36 minus cosecant squared theta pi over 4 pi over 2. And that gives that is just going to be equal to negative 1 minus 2, which is 1. So the whole thing just evaluates to 36. Okay. Next one. So for this one, our region is some little crackpot triangle, it looks like. So let's see. So we've got y going from 1 to x. So here's y equals x. And we're going from 1 to x. So let's draw the line at 1. So our y integration is going first. So that's this here. And then how far do we go? We go to root 3, which is, I guess, not much further than 1. So this is going to be 1 also. And then this is going to be root 3. Okay, so that's what we've got for our silly little region. And let's see, so drawing that again from the point of view of polar spectacles. Let's see, so this bottom one here is the corner of a 30, 60, 90 right triangle. So that's pi over 6 of an angle right here. So we're going to go from pi over 6 to pi over 4. This one being pi over 4. And then we're going to go from the horizontal line to the vertical line. So the horizontal line here, that's going to be y equals 1. So that's going to give us r sine theta equals 1. So we're going to have cosecant theta to start. And then to finish, we are going to have this vertical line right here, which is x equals root 3. So that's going to give us root 3 secant theta. And so now we just got to integrate this sucker. Man, yeah, doesn't this look so much better now that we've converted it into polar? That was a bad idea. I don't know who thought up this problem. It wasn't me. I refuse to take the blame. I mean, I guess I have to take the blame for assigning it, but I didn't make up the stupid thing. Okay, so this is going to be, let's see, so we've got integral pi over 6 pi over 4 of, and then we've got 1/2 r squared evaluated cosecant theta root 3 secant theta theta. So that gives us 1/2 integral of, and then we're going to get 3 secant squared theta minus cosecant squared theta d theta, and so that integrates up to giving us 3 tangent theta minus cotangent theta. By the way, I would not assign a problem like this without providing you, I mean on an exam anyways, without providing you with the necessary trig formulas. I don't, for the integrals. I would not expect you to have all these memorized. So we've got 3/2, 1 minus 1 over root 3, minus 1/2 minus 1 plus root 3, which simplifies all the way down to, and now I'm out of room again, 2 minus root 3. All right, the next one. Okay, so this one here, what do I see? So this guy, so this is telling me y starts at minus square root 1 minus x squared. So that's the unit circle, and it's the lower part of the unit circle. So we are here somewhere. And then the other part tells me that we're looking from minus 1 to 0. So it's this region right here. Okay, so setting this up in terms of polar, then I'm going from pi around to 3 pi over 2, and it's just a polar rectangle, aka I'm going from 0 to 1 all the way around. So I've got pi, 3 pi over 2, 0 to 1, and then I've got 2r over 1 plus r dr d theta. By the way, since the integrand is rotationally symmetric here, I could actually swap out these bounds of integration with 0 to pi over 2 and just pretend that it was up here instead. If doing shortcuts like this makes you queasy, then don't worry about it. I'm just saying that's a simplifying thing you could easily do if you wanted to tone it down a notch. Okay, so let's see. So in order to integrate this, I would probably do polynomial long division and say, okay, so if we do 1 plus r divided into 2r, then it's 2r plus 2. And so we get that the integrand splits into, let's see, so I've got 0 pi over 2 d theta. And then here we've got, this just became integral from 0 to 1 of, and then from our polynomial long division, we have 2 minus 2 over 1 plus r. And so that's pi over 2 from the theta integral. And then for the other one, integrating 2 is going to give us just 2. And integrating the other one is going to give us a log. So log evaluated from 1 to 2. So we have just the log 2 part remains. The log of 1 part is 0. And that's our answer there. And for the last one, let's see what's going on with this guy. We've got, let's see, so just decoding this one right here. This is y equals square root 2 minus x squared. So x squared plus y squared equals 2. So it's a circle of radius root 2. So we've got something that looks like this. And we are going, let's see, so this is done with the y direction first. So we're going vertically from y equals x up to the circle. And it's in the positive part, so it's got to be this part over here as opposed to, say, this part over here. It's not that part. And I can see that by looking at these guys. Okay, so now setting up this region in polar, we're going to be going from theta is apparently going from pi over 4 to pi over 2. And then we've got our radius going from 0 to root 2. And then we've got some chunky integrand, which, let's see, so each of those has when I put x equal to r cosine theta and y equal to r cosine theta, they each have a coefficient of r, so I can pull that out in front. And so then I have cosine theta plus 2 sine theta, dr d theta, and there's an r for the Jacobian, and I'll just put that over here on top of the r that I already have. And so let's see, so this one we can fubinate, and this is going to be let's see, so we've got the r cubed over 3 from 0 to root 2 times, and then we can integrate cosine and get sine minus 2 cosine theta from pi over 4 to pi over 2. And then let's see, so that first integral with the r cubed is going to be 2 root 2 over 3, and then at the bottom it's going to die, so when we put 0 in for r. And then, so what do we have for the other stuff? So we've got sine of pi over 2 is 1 minus cosine there is 0 minus, and then we've got it's going to be 1 over root 2, and the cosine is also 1 over root 2, but it's got a 2 in front of it, so it's 2 over root 2. And we're getting there. So what do we have? Combining the 1 over root 2 terms and multiplying this root 2 here, we can distribute this across, and we get 2/3 root 2 plus 1. Math!